Today we want to talk about complex numbers and specifically Euler's formula, which is e to the power of I theta equals to cosine theta plus I sine theta. So there are some stuff in math that we have something in a subset or in a small set, and then we generalize that in such a way that all the rules that we have already for the small subset still applies, but there are some other stuff that comes with the bigger set. So we have real numbers, right? I mean, if I have if I have an axis, I can say that this is 1, this is 2, this is 3, and so on and so forth. And then any number in between are represented by a real number, right? Then I multiply, I define addition, I define multiplication, and all the stuff that comes with real numbers. So what if I define an ordered pair, meaning that I have two real numbers and I put them next to each other and I make a number which is two-dimensional. So far I had one-dimensional number that it is a point on a line. So now I need I want to define two numbers. I mean, sitting next to each other, and it is like a two-dimensional number rather than one number, two numbers. And I define it as an ordered pair, meaning that I can't switch this A and B. I mean, mathematically, it means that if AB equals to CD, it means that A equals to B and B equals to D. So in other words, if I have AB equals to BA, it means that A and B are equal. So I can't change them, the order. So this is ordered pair. There are some other definition as, for example, I can define it in as a set of A and B. So you see, I can't switch the order of A, B. So anyway, I define an ordered pair made out of two numbers. So in a sense, I'm defining two-dimensional numbers, all right? So now I define addition between these two numbers like what we would expect as A plus C and B plus D. Multiplication by a real number, let's say I multiply by R, then R, A, and B equals to RA and RB. So nothing out of, place here. So I define addition for my two-dimensional numbers because I want to be able to do some math with these two-dimensional numbers. And I define a multiplication between these, two-dimensional number and a real number. So if I look at it, everything would be fine if I have one-dimensional number. In other words, if I have a one-dimensional number or a real number, I can define it R and 0 in two-dimensional numbers, right? So one-dimensional number would be special case of two-dimensional number when the second argument is 0. It's like, for example, square is a special case of rectangular. So this is when this is 0, a real number, right? So the addition that I had for real number, it still works because I add these two real numbers and these are 0. So again, it becomes 0 and two real numbers. Addition of two real numbers becomes again another real number. Multiplication, the same thing. So everything is fine. I generalize that notion of one-dimensional number to two-dimensional, and everything that we had for one-dimensional number, it still holds true. So now that I have this multiplication and this addition, what if I want to define, because remember I can multiply two numbers, right? Two one-dimensional, two real numbers. So what if I can define multiplication between these two numbers, even though they are two-dimensional. So what if I define it this way? It gives me a lot of structures. There are various ways to define that. One way that gives me good structures and a lot of good things comes with this definition later is that I define it this way. It would be AC minus BD. For the first argument, it would be this times this minus this times this. And for the second one, it would be this times this, AD plus BC. All right? So I define multiplication this way between two ordered pairs of real numbers, all right? So I can see that if I multiply, let's see, if I multiply 0 and 1 with itself, 0 and 1. In other words, I'm saying it is 0 and 1 to the power of 2. But this time, the power is not like the power that we had before. That's, I mean, it would be a real number. It is this, I mean, multiplication, twice of this multiplication, this type of multiplication, not previous type with the real numbers. So if I do that, I would have, you see, I would have 0 times 0 minus 1 times 1, so it is negative 1, and then 0 times 1 and 1 times 0, both of them 0, so 0 and 1. And this is familiar. This is like real numbers because the second argument is 0, right? So this is, I can write this as negative 1 as well, right? Just shorthand for this one, because this is a special case. We went, it's like we had something in rectangular and it became a square. So I can write it as one-dimensional number because the second dimension is 0 and we said that this is that thing. So you see, I have this to the power of 2 equals to negative 1. So in other words, let's write it 0 and 1 to the power of 2 equals to negative 1. So in other words, I can write as 0 and 1 equals to square root of negative 1. It's like, although this square root is opposite of this type of multiplication, it's not like square root that we had in real number. This is not, for example, square root of 9 would be 3. That is in one-dimensional sense of square root. Square root is the opposite of to the power of 2 multiplied by itself. This is not that. This is square root in two-dimensional. So it is not as if all of a sudden I have square root of negative 1 defined. It is not defined for real numbers. That is a bad thing that, I mean, at the beginning, I mean, historically, they thought that, okay, let's assume that, imagine that this number exists. Then this polynomial has root, and this name imaginary stick and stuck, and everybody is using that. But there is nothing imaginary about that. It is just two-dimensional number, and this to the power of 2, according to this definition, becomes negative 1. And this square root is for these two-dimensional numbers, all right? Now, after a while, we will see that, okay, rather than using this, because I can use this property, and if I call this I, then rather than defining this all the time, I can simplify the writing as A plus BI. I mean, simplify this multiplication as A plus BI and C plus DI with the condition that I times I becomes negative 1. You see? So if I write it this way, I would have AC plus BDI squared, which is negative 1. So the real part, it would be AC. I mean, the first part would be AC minus BD. And then I would have plus AD plus BCI. So this makes the writing easier. So with the condition that I square becomes, or this means I square equals to -1, right? With the condition that I squared becomes -1, I can write it this way. In fact, under the hood, it is doing this ordered pair multiplication. But this makes the writing and calculation easier. In fact, we're dealing with two-dimensional number. Probably some of you had some, let's say, hesitancy that why we put imaginary number in two dimension. Well, that is because it is two-dimensional numbers. We call the first part real and the second part imaginary. It is not imaginary, but the name stuck historically. So it is, let's say, for example, A and B, it would be A in the real part, and then B in this second coordinate. So this is that, let's say Z, which is A and B. This is my complex number in two-dimensional plane. So again, for one-dimensional plane, I have one point on a line. For two-dimensional numbers, I have a point in a plane, and I can define multiplication in two-dimensional number. And it turned out that that square root for that two-dimensional multiplication, it has a solution, even a square root of -1. Because when I define multiplication this way, this times this becomes -1. Now let's see what is e to the power of I theta. Well, it's not totally true what I'm going to say, I mean, historically, but imagine that it is relatively correct and true, but they come up with that e to the power of x from various angles, but I want to explain one of them. Let's say you know that the derivative was of interest for a lot of applications. For example, derivative of x2, it would be 2x, right? And for example, sine of x, it would be cosine of x, right? Or x to the power of 6 would be 5x to the power of 6, x to the power of 5, right? So the next question that comes to mind is that, well, I start from function, I get some other function. What if there is a function? Is there any function that I can do the derivative and get itself again after derivative? Well, you can start from this. Let's call this f of x, and I say that this would be 1 plus x to the power of 2 over 2 factorial plus x cubed over 3 factorial plus x4 to the 4 factorial, and I go on forever, all right? Well, then I see that if I do derivative, this becomes 0, then this becomes 1, this 2 comes out and down, and this 2 factorial is 1 times 2, right? 2 cancels out, so I would be left with x. Then this 3 comes out and down, 3 cancels out this 3 in the 3 factorial, which is 1 times 2 times 3. So it would be x2 over 2 factorial plus x3, the same thing, 3 factorial, and goes forever. So you see, I make every term again. So this equals to that, with the condition that this should be well defined. If it goes to infinity, it has no meaning. There won't be a function if this goes to infinity. But it turns out that this will be, this converges for any x, meaning that this would be a number at the end of the day, because this denominator grows way faster than numerator for any x. For example, 4 factorial, n factorial is way bigger than, for example, x to the power of n when n is large enough. And also the whole sum also converges. So this would be a well-defined function. Then let's see what happens if I put x equals to 1. I would have 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial, and all the terms. then it turns out that this would be a number 271 and some other eight, some other digits. So it is not a rational number. I mean, it can't be written as I mean, quotation of two real numbers. So it is irrational number. All right, so I would have this as, I can write this as sigma 1 over n factorial, n goes from 0 to infinity. So this would be an irrational number, and we call that E. So it turns out that this f of x, I can say that it is e to the power of x, all right? This is a function that can be written as 1 plus x squared over 2 factorial plus all the other terms, all right? So because when I put 1, it would be e, so e to the power of x would be this number. Now, I have this multiplication, so I can generalize. I mean, what prevents me to, instead of putting real number here, put complex number, and I use this multiplication in the sense of this ordered pair. So if I have e to the power of I theta, then it would be 1 plus I theta plus I to the power of 2 becomes negative, right? So I would have negative theta squared over 2 factorial. Then again, I multiply by another I theta, so plus I, well, minus I theta cube over 3 factorial. Then I multiply by another I, so this time it becomes negative again 1, so it is positive theta 4 to the power of 4, 2 over 4 factorial, plus I theta to the power of 5 factorial, then again minus, and so on. We keep going, all right? So now, let's use this part. I can pick these real parts, these parts that they don't have I, so it is 1 minus theta squared over 2 factorial plus theta to the power of 4 over 4 factorial minus theta to the power of 6 over 6 factorial plus, and for the imaginary part, you see, I factor out this I, and I'm left with theta minus theta cube over 3 factorial plus theta to the power of 5 over 5 factorial minus theta to the power of 7 over 7 factorial, and all the other terms. This is Taylor series for cosine theta, the first. And this is Taylor series for sine theta. And by the way, if you forgot Taylor series, I can write f of any x at any x as f of 0 plus x over 1 factorial f prime evaluated at 0 plus x to the power of 2 over 2 factorial f double prime evaluated at 0 plus all the other terms x cubed. So if I put 0 and I mean cosine of theta, then I would have cosine of 0, which is 1. And then this becomes sine of 0, which is 0, again becomes negative cosine. I mean, this becomes negative sine, and then this becomes negative cosine. Then it would be, you see, I would get the second term. I would have negative that, and then all the other terms. And if I plug in sine, I would this one would be 0, then this one would be theta. You see, I make all these steps. So it has nothing to do, this Taylor series has nothing to do with um, complex numbers. So again, there was nothing magic about it. There was nothing out of blue about it. I mean, it was just I defined two-dimensional multiplication. And then I use the fact that e to the power of x, that series, that power series. I mean, this is how we define e to the power of x. This was one way that originally mathematician came with the idea of e to the power of x. There was not, it was not the only way, but let's say, I mean, this was the thinking. We were looking for a function that its derivative equals to itself and come up with a series, and it happens to converge, very well behaved. So we call it e to the power of x, because e to the power of 1, it becomes all ones, and it becomes 2.71, and 818, all the other digits. I mean, it is irrational number. You can go up to infinity. Then we use this multiplication instead of one-dimensional multiplication for real number. Use this definition, because this is, it's like we generalize that notion of e to the power of x. As a matter of fact, later in control, you might see that even we have e to the power of 2 by 2 matrices. For example, let me write it a little bit bigger. So we can define e to the power of even 1, 0, let's say -1 and 1. E to the power of a matrix. Well, what does that mean? Well, again, we put these matrices here instead, and matrix multiplication is well defined, right? So I can have this in a shorthand, and the derivative of e to the power of a matrix would be the same thing. I mean, we use some properties of derivative of e to the power of a matrix. So why this is very useful, these complex numbers? Well, historically, they wanted to find solutions of a polynomial, right? So you might know that, for example, this polynomial doesn't have solution, meaning zeros in real numbers, right? But when I go one step above and define two-dimensional numbers, then this would have solutions, right? I mean, if it was, then I would have x equals to -10, then x squared, so x equals to square root of positive minus square root of -10, right? Or square root of 10 times I, right? So it has solution in when I generalize my notion, multiplication, and I go to two-dimensional numbers. Then they thought that, well, what if I have, now that I went up to the two-dimensional numbers, what if I have complex number even as coefficients here? Then, for example, instead of x squared, I would have 5ix squared. Do I have to go to higher dimensions yet? Because previously that I had real coefficient, I had to go to two-dimensional numbers in order to have solutions for every polynomial. As a matter of fact, if our polynomial is degree n, in this case it is degree 2. If it was degree n, we would have n solutions or n zeros, right? Now, what if I have coefficients that are complex themselves? Well, it turned out that you don't have to go to higher dimensions. It still works. So that is called fundamental theorem of algebra, and it means that when you have a polynomial that all the coefficients are complex, it has, if it is nth degree polynomial, it would have n solution in the complex plane. But that didn't prevent people to go to higher dimensions. As a matter of fact, Hamilton defined something like quaternion, and that is four-dimensional numbers. So we would have the first one real, for example, 5, then some imaginary number, I mean, second coefficient, then third coefficient, he used j, so let's say 1j, and negative, for example, 6k. So we would have four dimension. This is real. This is the first I, j, k. So we have even higher dimensional numbers. So, but for us and as engineer, if we generalize that one dimensional to two dimensional, there are a lot of good structures and there are a lot of good stuff already coming with that, and we didn't need to go to higher dimensions. All right. All right.